Today, I'm going to deal with I'm trying to disable annotation so that people can be able to get me. So, welcome to our today's sessions, of course, from the Yopa Command Center. And of course, these are again the second session of the National Chemistry Capacity Building for students who are waiting for KCSE. This is purely for candidates because the content that I'm going to unpack or rather illuminate today is a little bit complex. We are going to do topical mapping using the extended syllabus surgical analysis. So here we are breaking down. So it's like wherever you pick a topic, you try to do look at the options. What can be tested in this particular topic? So that one is called extended syllabus surgical analysis, or rather extended, apart from the normal syllabus that you know. You pick every topic and you see what is the content, what is the examination content in that, and you do it in such a manner that now you are able to exhaust all the possibilities in which the examiner can think. So today, I'll focus on a very important topic, that is the topic of rate, topic of organic, and possibly, is normally organic and rate. But from there are also some areas that maybe we find that the students are getting confused. Here we are dealing about, I'm muted, no, I'm not muted. So I thought I was muted, but of course I can see I'm not. So whatever I'm talking about is that I'll be able to take you through several areas according to the question that people have been talking about. Many students have also requested me to take them through the source. I'll also be able to see by the end of the day. I'll communicate that whether we are going to have a topic on rate, or rather analysis of rate, possibly by tomorrow. So we'll get ready in sections. Remember the video is also live in YouTube. Just in people accommodate 1,000. People can follow up conversation in YouTube, and they are asking. I think that one can put it. As I said, a clear version that you can be able to print, and I put them. I did put a clear content in there via my Twitter, because we cannot have students in WhatsApp, so we can only put something that the YouTuber cannot be able to post something like an image there, but I decided to post most of those summarized notes. I was able to put them in my Twitter handle. So when you go there, you'll be able to download, then you can print, and possibly you can use it in school. Thank you. Let's get ready so that we can be able to get. And I think you have also followed the recording. Those who missed yesterday, I posted it in my YouTube. I try to make it better. I will also do the same today. So please follow it up. So let's start. Let's start. So first thing is that we are talking about the rate of variation, and we are going to unpack the key concept. So we are focusing on the key concept and rate, and we are looking at the common mistake that students make when they're answering questions on rate. And again, I believe that you're following me, and of course you're able to hear me clearly, and the sharing of the screen is clear. Is that correct?
Yes.
Yes.
Perfectly. Yes. So let's try to illuminate and demystify this concept. So the topic that I'm going to deal with today is rate, looking at the key concepts, the concepts that are tested, the common mistake that students make. I'm also going to navigate through the organic examination content using the Octopath revision model now. So here we are doing now today. Yesterday, I took you through the content topical mapping, but today we are looking now at the question method. After now you have revised the topic using the notes, now you go back to the question. But you find that Sometimes you may find a book, like in the octopus book, as about 86 questions. You're going to find other revision book with 200 questions. But I can tell you for free, if you pick, you cannot be able to go through 100 questions. Somebody using Oppo 1K, you are nuisance to us. And I forgot to tell you the terms of engagement. You need to remain civil. You need to remain normal. We don't expect to see any abnormal in the chat. Yesterday you behaved very well. Remain muted, and if you want to ask a question, possibly put in the chat. If you want to ask a question, you can also unmute yourself and ask the question. Maybe ask for interruption. Then from there, the teachers on the wall will be able to alert me if there is any need that I need to respond. Whatever I'm saying is that now you find this now the revision technique is very simple, and it is the essence of the octopus revision technique that now you pick one question and you are able to exhaust everything. You are able to have to expect everything that is related to that particular content, because you may not have enough time to revise 200 questions. So let's see. I'll also be able to have a look at now the polymerization and detergent. These are an area that many students find is very difficult. I'll be able to show you how to be able to understand the concept of detergent. Very easy, using a very short note. So let's look at that. One, we look at rates. Before I go to rate now, the first thing on rate, you look at the factors affecting the rate of reaction. Like, let me ask you, how does concentration affect the rate of reaction? A student to answer that question. How does concentration affect the rate of reaction?
Yes, Mwalimu.
Yes.
I can answer that question.
Yes, you can answer.
So it increases the number of reacting particles, hence increases the chances of effective collisions, and which increases the rate of reaction.
Very good. Thank you. That is somebody is coding a late, but what is your name?
Victor.
Victor, good. So that's the correct way. Many students, they'll say increase in concentration, increase the rate of reaction. That is exactly what your grandmother will say. Your grandmother will never stepped in a chemistry class. So there is no chemistry in such a statement as increase in concentration, increase the rate of reaction. There's nothing like that. So in that kind of a scenario, like Victor said, you have to tell us, how does the concentration increase or decrease bring about more effective collision? You cannot talk about rate of reaction without talking about effective collisions. Just for example, for the students who are here, even everybody who is there, for you to come to this world, your father and mother should have collided with sufficient enough activation energy to bring about a chemical reaction whose product is you. That is chemistry. That people are, for example, even when you talk about reproduction, a man and a woman have to collide. They cannot bring about a new being, or rather a new offspring, by simply looking at each other and smiling at each other. So there must be an effective collision that will bring about a chemical reaction. So that is why I'm telling you that now we need to be able, that thing is very common with most of the students, whereby they just say, increase in concentration, increase the rate of reaction. So this is how you answer it. For concentration, you talk about increase concentration, increases the number of reacting particles in the system, leading to more effective collision. So here we are talking about increase in concentration will increase the number of reacting particles in the system, leading to more effective collisions. Another one, we can talk about pressure. As you can be able to see for pressure, the pressure will bring the reacting gaseous particles closer to each other, and that increases chances of effective collision. So This pressure brings the reacting gases closer to each other, leading to more effective collisions. The concept of temperature, I've always told students that you can even use the analogy of a cow on heat, whereby you find when a cow is on heat, it bellows. When a cow is on heat, it bellows. It produces a very funny sound when it is now the mooing, when it's bellowing. And the same sound is perceived by any bull nearby who notices this cow needs to undergo neutralization. So the bull will also respond by bellowing back. And according to the commandment and rules of animal reproduction, the first bull to respond, no other bull should also respond the same. So what will happen now, when the cow bellows, a cow which is on it, and the bull bellows, they start running towards each other, communicating more, I'm here, I'm coming, just wait for me, until they come closer to each other. They collide of course, remember when the bull reaches the cow has been suffering and need to be neutralized, will just say, take me, Lord. And a collision occurs between the cow and the bull. A white precipitate is formed, and that is an effective collision. There is no longer heat with those kind of things. So whatever I'm talking about here is very simple, that whatever you're answering questions on effect on temperature, effect of rate, effect of concentration, always remember that you have to tell us, how does that fact affect? So for purposes of temperature, you talk about increase in temperature, increasing the kinetic energy of the reacting particles. They vibrate faster, and that increases the chances of effective collisions. So those are just the issues that you need to talk about. And number two, we also talk about for concentration. Remember concentration, we are talking about only for aqueous solutions. Somebody will tell you like a scenario like a reaction between calcium carbonate and dilute HCl. Then the examiner will ask you, how can you increase the rate of reaction between calcium carbonate and HCl? And then a student will go and write by increasing the concentration of the reactant. That student always gets that question wrong. Why? Because you cannot talk about concentration of calcium carbonate. You say you increase the amount. For solid is for amount, not concentration. Are we together, students? I think I'm clear about that.
Yes.
Yeah. So that's something that's a trick. So, but you can use the word amount, which applies for all of them. But concentration cannot apply for solid. Or even gas, you talk about for only aqueous solution, talk about concentration. For the others, amount. Then the other thing, when you're told, how do you increase the concentration of calcium carbonate and HCl? Another student will say, by increasing the temperature of what? That is not an answer. You tell us now, can you increase the temperature of calcium carbonate? No. When you are now doing that kind of a reaction, properly what you need to do, you simply warm the acid. So you say, warm the acid. That is the way to talk about. In fact, talking about increasing the temperature is a vague thing. When we talk about it is something that's a physical activity. When you tell somebody by warming the acid, at least we are clear. The examiner can know that's a very good statement. That's a good framing of the answer by warming the acid. If you're using calcium carbonate granules, you can say by using calcium carbonate powder instead of granules. That's how you answer those kind of questions. And I think I'm clear about that. You can also talk about the size of the particles, whereby we talk about now small size particles have a large surface area, and that increases the chances of effective collisions. The other thing that is mentioned there is the catalyst, and catalyst lower the activation energy of the reacting particles, leading to more effective collisions. And it's very simple. Like when you're now cooking and you're trying to light up firewood, sometimes you apply paraffin. Ama watu wakitaka kuchoma mwizi wanachukua tile wanamwagia petrol. The petrol is like, it is acting as a catalyst, but it's not a catalyst per se. It is just an analogy, because remember now, realistically, we cannot say petrol is a catalyst, but that's exactly what a catalyst does. When you apply, when you pour petrol into firewood or into a tire, vehicle tire to so maybe when you want to, when people are burning those rather those two tips, it is simply makes it easier for the tire to burn, for the firewood to light up. So that is exactly what a catalyst does. It lowers the activation energy of the reactant. Simply, the activation energy is the minimum energy required to bring about a chemical reaction. And I think I'm very clear about that. Those are some of the issues that students do, and we don't want to talk about them. So then the next is when you're told to draw a diagram, and the student are told this is the total mass of the product, maybe this calcium carbonate, then the against time, then a student is told, this is something that is very common with the student. So when they are told to draw, like for example, something is taking place at a higher temperature or higher pressure, when they are told higher, they draw it like that. Sorry. They draw it like this. Then it goes above. So this is wrong, whereby somebody draws something that is, if you talk about a reaction, there are two reactions. One taking place at lower pressure, another one is a higher pressure. So many students think because this one is at higher pressure, they are supposed to produce more of the product. The product remains the same. The only thing that changes is the what? The only thing that changes is the time taken. So a faster rate of reaction, the curve will be very stiff. Stiff on the left means the rate of reaction faster. If you're using a very low pressure, then the reactant will be on the right and the curve will be gentle. And it applies for all of them. That's the only thing that you need to understand, that whether you're plotting higher temperature, higher concentration, the higher concentration is faster rate of reaction. It will occur on the left and the curve will only be stiff. That is the only thing, whether it is a catalyst, whether it's without a catalyst. But remember, for a catalyst, sorry. For a catalyst, there are two curves. Whatever I'm saying that when you're drawing graphs of rate of reaction using different variables, or rather by varying either the concentration, varying the pressure, varying the temperature, make sure that the curves are flattening at the same point. We should not have, just because we are using a higher temperature, because we are using a higher temperature, it doesn't mean that the product will be higher. Like for example, which one is easier to use, or rather which one is faster, using a gas cooker or an electric heater?
Electric.
Electric heater.
That's wrong. The gas cooker is faster than electric heater, practically.
Why?
How?
Because you see now, like, let me explain. First of all, how many minutes do you require to light up a gas cooker? Seconds, isn't it?
Yes.
But what about electric heater? Electric heater, we have the coil. So first of all, we have to, the coil has to become hot fast. It takes time. Just go and do it. And weke kikombe moja ya maziwa kwa sufuria, the same size of a sufuria. Another one kwa electric heater. First of all, the coil, lazima, the coil for the electric heater has to take time, so because before it becomes hot. So that now the heat now can be transferred now from the coil, the electric heater coil, now to the what? To the sufuria. But for what? For the Bunsen burner, for the gas cooker, the burner is just going to light in a second and the flame is ready. Are you getting the point?
Yes.
Yeah,
Yes,
that's the
we are
point.
getting
That's some, people just assume.
Yes.
That's what you call a fallacy. You continue using so many things until every now and then. Right? But it's wrong. Simply because many people do not use the electric heater because of one or two reasons for that. So it's very much important for you to be able to get that. Now, whatever I'm saying is that don't draw a curve just because you're talking about there's a catalyst. Then you tell us now, because here we are using a catalyst, the reaction will be faster. And on top of being fast, it will also produce more of the product. No, it cannot. The product remains the same. The only thing, if you are cooking githeri using 1 kilogram of maize and 1 kilogram of beans, and you are using, somebody is using firewood, another is using gas cooker, another one is using electric heater. The only difference, the volume of githeri you are going to obtain, because the reactants are the same, will also be the same. The only scenario whereby we produce a higher volume is when we are using excess solid reacting with a dilute acid. Like we can have excess calcium carbonate was reacting with 1 molar HCl. So what does it mean? In Amanisha, when the calcium carbonate was reacting with HCl, did all of it react?
No.
Did not react.
No.
So
No.
now in that kind of a scenario, to assume to produce this kind of the curve. But now you repeat the experiment using 2 molar hydrochloric acid. So if you're using 2 molar hydrochloric acid, if you increase the concentration of the acid, in Amanisha, there is more of the acid molecules. And the calcium carbonate was also in excess. So what are we going to produce? We are going to have a more product will be produced because we have increased the concentration of the acid, meaning we have added more of the acid molecules, and there was unreacted calcium carbonate. So therefore, more carbon dioxide will be produced. So that is only now when you're told to draw the curve of change, you're going to draw the curve on the left, being more stiff, and also it is not going to meet at the same point. It is going to flatten at a higher level, meaning that more product is produced. For those who have used the Guru, you have also been able to get that. So those are the only difference. Then we also have the catalyst. We can also use the concept of energy level diagram to represent. So catalyst is the graph of effect of catalyst on rate can also be represented using either this a straightforward normal rate of reaction graph or using what you call the thermochemistry graph. And that's whereby you're going to have reactant and product. Then you talk about the activation energy. Without a catalyst, we are going to have higher activation energy. More activation energy will be required without a catalyst, and less activation energy will be required for the catalyzed reaction. The maximum energy structure, this one now is called activated complex. Not, many students, this one was asked sometimes in KCSE 209, and they were told to name label structure X. And most of all the students were saying this is called activation energy, which is wrong. So the maximum energy point along the reaction path is called the activated complex. So how do you get the activation energy? You get the energy of the activated complex. This is the energy of the activated complex minus the energy of the reactant. That is how you get the activation energy. So in short, I'm saying the maximum energy, the tip. I've said the maximum energy structure along the reaction path, the maximum energy structure along the maximum energy point along the reaction path is called activated complex. How are you getting the activation energy? We are looking at this energy here, activated complex minus energy of the reactant. That is how you get the activation energy. So it's just the tip. The top of the mountain. So here, this top here is what you call the activated complex. Are we together?
Yes.
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 Perfect.
Yes.
I think now that one is understood. Very magnetic. We can continue. Now, another concept that students do not know is how to calculate rate at a particular point. This is called instantaneous rate. Ukiambiwa calculate rate at 8 seconds. Like you see, calculate rate at 8 seconds and also calculate rate at 25 seconds. So when you're told to calculate rate at 8 seconds, unakuja hapo angalia 8 seconds ndio hii, then you draw a tangent that is touching that 8 seconds. That is in touch with that. So you draw a tangent. By drawing a tangent, that is the first marking point. Then you calculate the gradient. Gradient is change in y, change in y over change in x. Let me use a laser pointer. Change in y, like for example, hapo unaona hapa in around that what? 36. That is y. Na hapa ni around 4. 36 minus 4. Then you go for the other one. The change in x is this one. This is 12 minus 0. Then you get the change in y. Remember, the change in y is the product. If it is now the gas produced or the mass consumed. So it's just going to be volume per second or grams per second. So that's rate, that is at minute 5. So I'm saying then at minute 25. At minute 25, you're going to look at this minute 25, you draw a target that is touching.
Oh, you can put a graph per second, eh?
Yeah?
You can put by graph per second.
Yeah, they can be gram per second. If now, here we are talking about gram, you know, sometimes it can be calcium carbonate reacting with HCl. In that kind of other, you're going to plot the graph of mass consumed per unit time. Are you getting the point? Eh? Are you getting the point?
Yes.
Yes.
Yeah, but now that curve will be looking like this. That curve will be different. It will not look like this. The curve now of decrease in mass will now look at something like this.
Excuse me,
Now
sir.
Yes?
Excuse me, sir. Your graph, you said 8 seconds, but looking closely, it's, I guess, 12 seconds. So I am getting confused, sir.
No, I'm saying curve ilikuwa hapa. Tunaelewana hivi, eh? So the 8 seconds is around here. Are you get the point, eh?
Yes.
Unaona?
Yes.
Unaona sasa?
Yes.
Your target imepita hapo, imepita bora imepita hapo. So maybe you may be, is not, the target is not here, it's not this point. I think that is now why you're getting confused. Are you get the point, eh?
Yes.
In fact, there is no target that is touching at 12 seconds because your line haijashika hapa. So when you talk about that target, it must be on contact with that curve at that particular point. But it can extrapolate. So you see, like for this curve, you see the curve is touching. The curve is touching the curve. The tangent is touching the curve at this. Hata bado ungekuwa hapa, hata ungesema 5. But the fact is now, the most important thing is like, it may be able to touch the curve at different points. But that 8 seconds must be one of them. Are we together?
Yes.
I'm still confused.
Yes.
Why are you getting confused?
It's about drawing these tangents. Can you please be a bit clear, because I'm not yet getting it.
So I'm saying, let me just get a blank thing like that. You have something like that, sorry. And this now we have a curve like this.
Yes.
Elewana? So
Yes.
this is now 5 minutes. To say you want to draw a target at 5 minutes. Are you together?
Yes.
It's now 5 minutes. So twende hivi tufike hapa. So 5 minutes equals somewhere here, isn't it? Huh?
Yes.
So then now you can let me get a different color. So now in that kind of, now just draw a straight line. That's now the target. That is now touching that thing at that point. Sorry, it's not coming out very clearly. But assume that is a straight line. Bora imeshika hapo. Tunaelewana?
Yes.
So it doesn't matter how long would that target will be. So unaweza chora kadogo, but finally now after doing that, now you can get the change in. Now from here, you can just join it. We just join it to make a triangle. For the marking point is only this. Making a triangle has no mark. Are we together? That's the target. You draw a straight line like that. Then you can now get the gradient by looking at, like now look at that. So this is now the change in, if that was our target, the change in Y, this is the change in Y. The change in X, we are going to pick hapo na hapo. That will be now the change in X. Are you getting now?
Yeah.
Yes.
That is very magnetic. That's good. And I like the fact that now you have stressed that I have not understood. It is okay. That is why we are here to simplify it. And I think now you have just understood. So you just, it doesn't matter. After your target ungechora tu, bora ime, hata kama ni short aje, it doesn't matter. So the length of the target doesn't matter. But of course, when you draw a tangent at that point, you get the change in Y over the change in X, then you get the rate. Then for change in 825, you're going to also do the same. But let me tell you, anytime you're going to find an examiner telling you to calculate rate at 5 seconds and at 10 seconds, the next question will be now to explain. So where is the rate faster according to this? At 8 or at 25 seconds? Where is the rate faster?
At 8 seconds.
At 8.
Why?
At 8.
Why is it faster?
The volume of gas being produced.
Okay, let me, for example, give you the reaction here is magnesium reacting dilute sulfuric acid. Magnesium metal react to dilute sulfuric acid, and here we are talking about volume of hydrogen gas. So why is rate at 8 seconds faster than at 25 seconds?
The volume of gas produced at 8 seconds is higher than that produced at 25 seconds.
Mm-hmm. Why?
Because
The
at
volume
8 seconds,
reactance is higher.
Yeah. Because what? I want to get the answer.
because at 8 seconds, the magnesium is at a higher concentration. Hence, there is a larger number of reacting particles, hence a larger number of successive collisions. While at B, the magnesium is less, leading to less number of reacting particles, leading to less number of successive reactions of successful collisions.
Okay. Has he got it right?
Almost.
Yeah.
Definitely.
Yes.
Sharon and Osembe, he is almost getting it correct, but there is somewhere he has messed up, and he has repeated the same mistake that I mentioned. Don't talk about the concentration of magnesium. We cannot talk about concentration of magnesium. Are we together?
Yes.
So we say at 8 seconds, the amount of reactant is higher. Therefore, there is more of the reactive particle leading to more effective reaction, hence faster rate of reaction. At 25 seconds,
Pardon.
just listen, I'm saying at 8 seconds, the amount of reactant, that is enough, amount of reactant is higher. Hence, more of the reacting particles, and more higher, or rather more effective collisions. At 8 seconds, the amount of reactant is higher. There is more of the reactive particles, and therefore we have more effective collisions. At 25,
Excuse me, teacher.
yes?
Excuse me. I'm asking, you must be slowly so that you can get you right.
Okay, can I repeat again?
Repeat again, yes.
Yes.
I've said at 8 seconds, the amount of reactant is higher.
Yes.
Therefore, more reactive particles, and hence more effective collisions. Is that one correct?
Yes.
Yes.
Okay, at 25 seconds, some of the reactant.
I have a question, sir. A question.
Yes.
Is it? Are we allowed to use, instead of saying effective correlation, Can we also allowed to say fruitful collision?
Yeah, they are the same, but you stick to effective collision, the most suitable terminology to use that is highly accepted in NEC.
Okay. Thank
Just
you.
the other day, 2020, they rejected, they started talking about we rejected successful and fruitful. They all remain the same, but just stick to the most suitable answer. The idea is, remember what I told you yesterday, what is tested, how it is tested, and what is expected. So always stick to the most suitable answer, the most suitable terminology to use.
Okay, thank you.
Thank you. So I've said at 25 seconds, it's just the opposite. Some of the reactants have been converted to products. Have you got that point clearly?
Yes. Yes.
Therefore,
Yes.
fewer.
Badu.
I want you to be keen so that you follow it with me. At 25 seconds, some of the reactants have been converted to products, right?
Yes.
Is that point on?
Yes, home.
Therefore, fewer number of reacting particles, therefore fewer number of reacting particles leading to fewer effective collisions. I think you are clear now?
Yes.
Perfect.
Repeat.
Hi. Good people, anyway, let me repeat again. At 25 seconds, some of the reactants have been converted to products. Clear?
Yes. Yes. Yes.
Therefore, there is fewer effective collisions. And therefore, I'm saying there's fewer number of reactive particles leading to fewer effective collisions. Remember, when you just say more effective collisions is synonymous to saying faster rate of reaction. So that's enough. You don't need to. By saying end faster rate of reaction, that is what we call tautology, unnecessary repetition.
The gradient.
Huh?
What if the gradient is negative?
Gradient negative. How? It cannot. It's not possible. I have never seen that kind of a scenario. Unless now when the reaction is over. Is somebody trying to get here and I'm not getting this? Oh, sorry. Take it in my hand. That'll be a minute, like there's something that is not working here. Take it in my hand. I'm not even able to see them. I want to move to the next. Just give me 1 minute. I correct something here.
Okay.
Yes, my fellow students, hi.
Hi. Hi. Hi.
Okay, now we are back and everything is okay. I think you're able to hear me.
Yes.
Yeah, there was
Yes.
Yes.
Okay. Now I think that one is clear about this, about the concept of rate. Don't talk about concentration of solids. Stick to amount. The word amount will apply for all of them, even liquids and even the liquids are solutions, gases. It's okay. That's a universal term. Now, the other one is the chemical equilibrium. Any students, when they're given this question and they're told to identify the forward reaction, they normally give this one. They normally give this one as the forward reaction, which is wrong. So the reverse reaction, you're here in there 0. The forward reaction, you're in there 2. That is when you can be given 2 graphs. One talking about rate, another one talking about amount. So forward reaction is this one, not this one. So the first one, the one starting from 0, is what you call reverse reaction. Because assume now you're having something like assume now you have a question like this. You have a scenario like this. We have maybe you have nitrogen gas reacting with hydrogen gas. Then this is a reversible reaction to form what? To form ammonia. So now, in that kind of a reaction, I just want to explain. When you are starting, do you have ammonia? Sorry. When you are starting, when the reaction is starting, do you have ammonia?
No.
There's no ammonia. That is why there is no ammonia decomposing to form nitrogen and hydrogen. So there is no backward reaction starting. That's why for the backward reaction, it is a 0 when we are starting, because this is time. Remember, we are plotting this one again is time. So at time 0, when the reaction is starting, there is no ammonia to decompose. That is why the reverse reaction starts at 0. But now, at the beginning, there is a lot of nitrogen and hydrogen. So the rate of the forward reaction is very fast. Ndio maana rate yake iko hapa juu, but hii ingine iko 0. Umeelewa?
Hapana.
No, teacher. Pardon, teacher. Pardon, please.
Okay, can I explain again?
Yes.
Maybe here we are having a reversible reaction. Na hii ni nitrogen na hydrogen to form ammonia. Sawa.
Yes.
The one
Yes.
is the formation of
Ammonia.
Ammonia.
Backward reaction is the one that involves the decomposition of ammonia to form nitrogen and hydrogen.
Correct.
At the start, we have a lot of nitrogen and we have a lot of hydrogen. So we have forward reaction is very fast, like very high here. When we talk about now, this one shown here high, the maanisha here the rate is very high here. Are we together?
Yes.
Because glass part kuna night let that do up the area that I know is good. Say ukianza to nitrogen hydrogen ammonia. So at the beginning there is a lot, the rate of forward reaction is very fast. Why? Because we have a lot of hydrogen and we have a lot of hydrogen. So the forward reaction is taking place to form ammonia at the beginning. Are we together?
Yes.
Yes.
So at the beginning, we only have hydrogen and we have nitrogen. So the reaction is taking place because there is no reactive particle. The reactive particles are there. But now for the backward reaction, which we call the reverse reaction, requires the composition of ammonia to form hydrogen and nitrogen. So at the beginning, we even have the ammonia.
No.
Ammonia. The rate of decomposition of ammonia is 0 because it's not even. Are we together?
Yes.
That is why the reverse reaction inaanzia 0 kwa sababu hakuna ammonia. There is no ammonia to decompose. So there is no, the rate of reaction, the rate of backward reaction is 0. But now as the time proceeds, nitrogen and hydrogen start react to form ammonia. So ammonia ni kidogo inaanza kudecompose pole pole. So the rate of backward reaction inaanza kuongezeka. But now the rate of forward inaanza ikiwa very high. But as more of the nitrogen and hydrogen is being converted to ammonia, the rate of forward reaction starts to decrease, the rate of backward reaction to start to increase until they are equal. At that point, we say the reaction has attained what? Dynamic equilibrium, where the rate of forward and the rate of backward reaction is the same. Meshika.
Yes.
Yes.
Meshika,
So
the good thing is usually is recorded and will also be repeated. So you can still listen to it again. Point is now you have known why the reverse reaction comes from. Because you don't have we together.
Yes.
So
Yes.
now these are now the same curve can be talked in terms of amount. So this one is very easy if you have understood this one. At the beginning, there is no product. To nitrogen and hydrogen forming ammonia. At the beginning, the amount of product is zero. Hakuna ammonia. So the ammonia starts at zero because it's not there. Are we together? Are we together, students?
Yes. I have a question.
Then just relax, then you'll ask a question. Then as the reaction proceeds, ammonia starts getting formed. So you see amount yake inaendelea ikiongezeka ammonia mpaka inaacha kuchange. Then reactants zilianza zikiwa mingi. We had a lot of hydrogen and nitrogen that are reacting to form ammonia. So the amount of nitrogen and hydrogen is very high. Then as the reaction starts and nitrogen starts to be converted to ammonia, the amount of reactants start to decrease until a point is reached whereby they no longer change. Remember, at the equilibrium point, the amount of reactants and the products do not change. They remain the same. Ukiambiwa, what are the characteristics of a dynamic equilibrium? The amount of the reactant and the products remain the same. And the rate of the forward and backward reaction remain equal. Are we together now?
Pardon. Again.
We are
Good.
together. We need to move fast so that we can handle many areas.
Characteristics of dynamic equilibrium.
Pardon, Mnabo.
Okay.
We need to be faster.
Yes. We need to be faster, but we also need to give those people a chance to be able to get some.
Then they have to begin.
Characteristics of a dynamic equilibrium.
What? The characteristics of dynamic equilibrium.
The amount of products is equal to amount of reactants.
The amount of reactants and products remain the same. And the rate of forward and backward reaction are equal. And whatever I'm saying, you people, they just the way like somebody telling you. If it's something that I have said, you'll also be able to rewatch the video, and whatever you not get, you can listen again. Senior Kweli?
Yes.
So can we proceed, please? Now,
yes.
And somebody's an a question that 98% of the students will get it wrong. State and explain the effect of increase in pressure on the rate of the following reaction. Answer. You can write in the wall very fast.
Oh, can I speak?
Yes.
The pressure.
No effect.
All of them, then we can see. Kate, talk.
The pressure, it favors, when there is high pressure, it favors the side with the less volume. And when you have when the pressure decreases, it favors the side where there is higher volume.
This reaction, how will pressure affect?
With increase in pressure, the equilibrium will be shifted to the forward side.
Wow.
There will be no effect. There will be no effect.
Pressure has no effect.
No effect.
No effect. Forward reaction. No effect.
There will be no effect.
No effect.
Now listen, students. Now you are the
An,
new pack.
an
Listen.
increase in pressure favors the side with less particles.
But it's
And
not
here we can see.
Let me.
This is not an equilibrium. An increase in pressure versus a decrease in volume.
99% of you have got that question wrong, and it is wrong. So the answer is this. Rate increases, that's the first marking point, tick 1 mark. Then explanation, an increase in pressure brings the reacting gaseous particles closer to each other and hence increase the chances of effective collision. Common mistakes, can someone read for us?
Common
Yes,
mistake
read
is
for
that
you.
most students
Common
will say no effect as the reaction is not accompanied by change in volume, losing all the marks. Students confuse rate of reaction and reversible reactions.
Hallelujah. You see, everybody is talking about equilibrium. Where is the equilibrium here? Have you seen any equilibrium here? You know the sign for equilibrium, eh?
Can I ask a question?
Yeah, yes, ask Kate.
Yes, so Chai, what do you mean by equilibrium? See, we always say that it shifts to the right side, hence favoring forward reaction. So I don't understand the common mistake in what we are trying to explain.
I'm saying in rate. When I was starting this session, I started with talking about rate. Kuna rate na kuna equilibrium. Are we together? Rate is a reaction like this. As long as the reactants are gases, when you increase the pressure, it will bring the reacting gas particles closer, leading to more effective collisions. Let me try to clear the air more. I know where the problem is coming. Just listen. Just follow up this one. Just relax so that I can now go to the next. Now look at that. Angalia swali sasa. State and explain the effect of an increase in pressure on the equilibrium below. Now, this is now the question most of you are answering now. Kate, are you getting the difference now?
Yes. Excuse me, Cha. Mwalimu.
Yes.
I got the question, yes. But I was asking, is stuff ya shift the equilibrium, the reaction is forward. Hapo hiyo explanation does he get?
Nasema, talk about there is no equilibrium. Equilibrium is we use this sign. That's when you know you are dealing with equilibrium. But now here we are talking about rate. There is a difference between rate. In fact, rate of reaction, that topic is divided into 2 components. There is the first component, the first segment is rate. Second segment is about equilibrium. So a question like this arrow is showing normally an equation that is not reversible. Are we together? So here, when the examiner talks about rate, we only talk about how does pressure affect rate. The first thing that we should have looked for here was, is this reaction involving gases? Yes. And if they're involving gases, automatically, if you increase the pressure, it will bring the reacting gas particles closer to each other, leading to more effective collision. I think I'm now here. Then, now for equilibrium, will bring a question with this kind of arrows. And with this one now, we are talking about state and explain the effect of an increase in pressure on the equilibrium below. And this one now you're going to say there is no effect because the equilibrium is not accompanied by any change in volume. Because here we talk about now the volume on the left here are 2. The volume on the right here are 2. So 2 volume, 2 volume. So the equilibrium should shift to the side with less volume, even if the pressure. Here the
Sure.
So, no. Yes.
So hii swali ni ati hii ni reversible, hii ni reversible.
This one is equilibrium. The other one was not equilibrium. It is simply rate. That's why I'm saying, because the teacher started with rate, kila kitu ukipe, na akamalizia na equilibrium, kila kitu ukipewa kwa mtihani unaonanga equilibrium. So that's why I talk about don't confuse rate of reaction with the chemical equilibrium. In fact, this question was brought in the year 2010, number 5, that is 2010 paper 2, number 5, C Roman 2, and 98% of the students got it wrong. Are we together?
Yes.
Yes.
Angalia, is it rate or is it equilibrium? You see, when people here were telling us the forward reaction, the back, where is the backward and the forward reaction here? Are you not even laughing at yourself? Are you seeing any equilibrium? Even seeing forward and backward reaction here? This question,
excuse me, sir.
One direction. That's correct now?
Yes.
Excuse me, sir.
Perfect. You know, I told you I'm dealing with the common mistakes and I'm navigating through the areas that can give me mistakes. And I think you have that. And again, Standard explain the effect of increase in pressure on the equilibrium below. Many students again will say,
excuse me, sir.
Somebody was asking something.
There'll be no effect because pressure acts on
effect. What we mean, solids and liquids have negligible volumes. What do you mean by negligible volume?
It means very little volume.
Very little, but not the same as zero. Tunaelewana, eh? So what to talk about here, which side has more volume there between the two? Solids and liquid have, so the volume there is almost like a zero here. The volume there is almost like a zero. Like a zero, but not zero. But this is one volume. Which side has more volume? Which side has more volume? In the left and the right?
Hapo sijaelewa hapo.
Right side.
Right.
Right side.
The right side.
Mwalimu, excuse me, mwalimu, hapo unaweza rudia kidogo. Rudi hapo sijaelewa.
I'm saying, nasema hivi. Solid ama liquid, they occupy a very small volume. So what happened is, iona ukipewa equilibrium, we are talking about with volume. Let's look at.
Yeah, pardon.
You know, the problem, most of you are not listening. Listen fast. Listen to understand. Say, if a solid has negligible volume. Negligible is synonymous to infinitesimally smaller, very, very, very small. So in that kind of a scenario, a solid has very, very, very small volume. So this side has very, very small volume. This side has very, very small volume for calcium oxide, but carbon dioxide is a gas, so it has one volume. So which side has more volumes than the other? The left or the right?
Right.
The right.
When you increase the pressure, the equilibrium will shift to the side with less volume, which is what?
The left.
Left.
Backward reaction favor. So increase pressure favor the backward reaction because it has lesser volumes. Just be guided this. For equilibrium, and I want you to listen again. For equilibrium, there is no effect if everything that is being used in that equilibrium is a gas or a liquid. No, is a solid or a liquid. If all the reactants, all the substances involved in an equilibrium is a liquid or a solid, then there will be no effect. But if one of them is a gas, there will be effect because that gas will bring about effect in volume. Tunaelewana?
Excuse me, Bwana Mbaluka.
Yes.
Yes, the state symbol for carbon dioxide, maybe it's confusing these learners. It should be gas, but certainly they are solid.
Oh, that is, I think, the problem. Gas. Yes, yes. Thank you for that. I think I had not seen that. That's it. I think that is also something that I think I had meant a mistake when typing. So that was a typo. This should be a gas. For it to bring up an issue, carbon dioxide is a gas and it has one volume.
Mr. Mbaluka, I have a question.
Yes, go on.
For such a reaction at equilibrium, should we be using volume only?
For pressure, you only deal with volume, and the volume that brings about effect the volume of a gas only.
Thank you.
So that's the point. Of course, I think students, you have got that point that there was that typo that carbon dioxide should be given as a gas and it has one volume. All the others, they are solid and they should occupy negligible volume, very, very small volume. So in that kind of a scenario, you are given an equilibrium. If given an equilibrium and one of it is a gas, then pressure will have an effect. But if everything was a solid, then there will be no effect. Another scenario that you need to also understand is that an examiner can also tell you what the effect of adding sodium hydroxide to the equilibrium, to this reaction. What the effect of adding sodium hydroxide to this equilibrium? Students?
Sodium hydroxide, the reaction will shift to the right. Because the volume of carbon dioxide will be consumed. Carbon dioxide will be reacting with sodium hydroxide.
Absorbed by sodium. Therefore, it leads to the right. That's the only thing that you need to talk about. The sodium hydroxide absorbs carbon dioxide, reducing its concentration. Therefore, the equilibrium. Okay. Look at that. Consider that equilibrium.
Excuse me, sir, I have a question.
HCl to that equilibrium.
Sodium.
What's the effect of adding dilute HCl? Somebody to give us the answer.
It will favor the backward reaction due to addition of more hydrogen ions.
Talk about observation. The key word is observation. That is what we are dealing with.
The orange color intensifies.
Orange color intensifies.
Because the orange color intensifies because addition of hydrochloric acid lead to in hydrogen ions. Therefore, they clear sheet to the left. So we talk about the orange color intensifies. What if it was sodium hydroxide? What will be the observation?
The orange color becomes less intense.
The orange color fades or rather dense, but you cannot say the colorless color intensifies. You only intensifies when the two colors are different. But that is, I can see students are very magnetic in this one. Now you prepare vizuri. Haya, twende next.
The orange color becomes less intense.
Yeah, becomes less dense or rather fades. That's okay. The next one, I think that is this one is now easier. When you add diluted HCl, what are we going to do with observation?
The brown color of mixture intensifies and the green color of the mixture fades.
No, for HCl, the
yellow color of the solution intensifies.
Just say the yellow color intensifies. That is enough. For sodium is going to consume the HCl, so the green color
intensifies.
Yeah. There are two things. For the first one, listen. For dilute HCl, you are going to say, when you add dilute HCl, the yellow color intensifies and more of the yellow solid dissolves. See now, when you're now shifting, there is also the yellow solid here. When you have a solid, don't say the yellow solid. You cannot say the solid intensified. You just say the yellow solid, more of the yellow solid dissolves. That's also the other observation. that more the yellow solution, the yellow color intensifies, and we also have a yellow solid. So more of the yellow solid will dissolve. Are we together?
Yes.
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 I'm shifting to the right. So the green color intensifies, and the more of the yellow solid is formed. So for solids, if a solid is involved in an equilibrium, and you're talking about shifting, if it's shifting the opposite direction, you're going to say more of the white solid dissolves. If it is shifting to the same direction, you're going to say more of the yellow solid is formed. Tunaelewana?